We saw some pictures. We saw specific motion diagrams last time. You can depict motion via a data table, right? If you can see patterns within that table, you can interpret whether things are speeding up, slowing down, all those types of things, looking at position versus time, all that kind of stuff. Okay, and then lastly, we're going to look at what's called a position versus time graph today. All right, a simple XY coordinate system, but we're going to be able to look at the relationship between the position covered and how much time that it took to cover that amount of space or distance or displacement. Okay? Every one of these single ways to look at motion can describe the same thing. Okay? They're all considered equal representations. One is not necessarily better than the other. Sometimes they look better than others, but they can represent motion in the exact same way. Okay? So let's start looking at our first main concept in physics, and it's velocity. Okay, velocity is change in displacement divided by change in time. Here's our equation for velocity. Your first physics equation. Aww. Sweet. You might want to write this day down in your journal. You know, I learned my first physics equation today. Okay, so sweet, right? All right, velocity is change in displacement over change in time. Can someone please tell me the difference between distance and displacement? Yeah, Nate, what do you think?
Displacement is distance from where you started and where you ended.
Uh-huh.
And distance is the amount covered.
Exactly. Displacement is how far you ended up from where you started. Distance is the amount of steps, the amount of feet, meters you covered during that particular path or that walk. What are two things that displacement has to have? Okay, yeah, starting point. Displacement is a vector, right? We talked about vectors. Magnitude and direction, perfect. Have to have magnitude and direction. Magnitude's the size, right? That's the number. Direction is telling us forward, backwards, up, down, east, west, all that kind of stuff, okay? So we've got to have both those things. Velocity is also considered a vector quantity. Velocity is a vector quantity, which means it can be represented by an arrow. It has to have two things, magnitude and direction. Okay? That's what a vector quantity means. It has to have magnitude, it has to have direction, and we can represent vectors with an arrow like this. Do we remember how we look at the arrow specifically for a vector? What's this end of it called? Tip. Okay, tip. And this end, Ryan, is called? Tail. All right. What's it called when we add those vectors graphically? Yeah, we get a resultant out of it, but what's the method called? Tail to tip, right? We add those vectors tail to tip, one on top of the other. Tail to tip method. That's one of our vocab words that we should have been studying in the past couple days. Yeah, okay. That's what I thought. Okay, so if velocity must have a direction included with it because it's a vector, what would it mean if we have a negative velocity? What would it mean if I told you I was traveling at a speed of negative 4 meters per second? Yeah, you're going in the negative direction, so I might be going west, or I might be going downward. Okay? Those are types of things that you look for. So this negative can be an indication of direction. That can tell us that we're moving backwards or in the negative direction. Remember, on our coordinate system, we always consider west to be negative and south to be negative, east and north to be positive. Okay, so our coordinate system remains the same as everything you've probably learned about coordinate systems in the past. So if I tell you I'm going negative 4 meters per second, it means I'm moving west or I'm moving in the downward direction. Okay, that's what we just talked about. Negative velocity is backwards or negative direction. Okay, our units for velocity are meters per second. Meters per second. So we need to be really good at identifying a variable from a word problem based on its units only. The reason for the units on velocity is that displacement is in meters. Time then must be in seconds. That's where meters per second comes from. We're covering so many meters in so many seconds. Okay, that's what velocity is. It's a rate. Okay, or length per time. You could have kilometers per hour as a velocity unit. You could have feet per minute. You could have any sort of distance per any sort of time. Okay, length per time. Okay, so let's go ahead and try one here. I'm going to give you a couple minutes to get this one written down if you choose to do that or to start thinking about it. We're going to walk through it here in just a second. All right, so let's start taking a look at our overall goal here. What in our overall problem, what are we solving for? Distance. So are we solving for displacement or are we solving for distance? Okay, distance, which means we don't really care about the direction. The direction doesn't concern us at this point, okay? So we're going to go ahead and break this down since we have a velocity and a time, and we have another velocity and another time. We're going to do this in two separate problems, and then we can just add those distances together. Okay, so first of all, we have a velocity of 50 meters per second east. That's equal to distance or displacement over time. What do I need to do with my time here? Change it from minutes to seconds, right? My units for velocity, displacement, and time have to match. So my displacement would have to be in meters, my velocity would have to be in seconds, okay? So 2 minutes is equal to 120 seconds, all right? And how do we go about solving for this variable d? Yep, we multiply these two numbers. So if I'm traveling 50 meters per second for 120 seconds, that means I should be traveling a total distance of 6,000 meters, and I went east. I went 6,000 meters east during that particular portion of my trip. Are we on the same page so far? Okay, let's look at the second portion of our trip. We're going to go south, and we're traveling 30 meters per second south. We're solving for displacement here. We also traveled this direction and speed for 120 seconds. All right, which means we traveled a total of how many meters? Okay. So now we've determined our total length or our total displacement east. We've determined our total displacement south. To find our distance, all we do is add those two together. Okay? So that means our total distance covered was 9,600 meters. And we don't need a direction because it's just distance. Distance only. 9,600 meters. Okay, any questions? All right, here's where we look at, take it one step further. What's our displacement now? What's our displacement? Okay, so I'm going to draw my coordinate system right here, and I'm going to make that origin my starting point. Okay, we traveled 6,000 meters east, so we'll say that's 6,000 meters east, and then we traveled 3,600 meters south. Does that make sense? What did I do to those vectors? I added them tail to tip. Tail to tip, right? My first vector started at the origin, went in the direction of my motion. Next vector adds right onto the tip of that first one, goes in the direction of my motion. So if I draw a, basically the sum of those vectors, what's it called? The resultant vector. The resultant vector is the sum of all those vectors. And your resultant vector starts where? origin and goes to tip of the last vector. Very good. So this would be our resultant right here. This vector right here would give us our displacement vector. This resultant vector is going to tell us our displacement because it's telling us exactly how far we're ending up from where we started. Okay, displacement doesn't need perfect, basically horizontal or vertical. Displacement can be both of those things. So this is moving at an angle, so it's going to have an angle that goes with it. Okay, yeah, Nate. Yeah, what do you think? Did you solve for R? 6,197, sorry, 997 meters. Okay, so that's the magnitude of our displacement. We solved the hypotenuse of this triangle, right? A squared plus B squared equals C squared. We're on the same page solving for R. Okay, now we go to that last little bit trickier part here. This is our magnitude of our displacement. What else do we need? Direction. Okay, and saying southeast is not a good enough direction.
East of south. South of east.
Still not quite. South of east. But we have to solve for that angle. Okay? Here's where we know if it's south of east or east of south. If we go east first, then we open the door to the south. We read it backwards. We went south of east. Okay, we went east first. Because it doesn't help us with our angle right here. We're going to solve this angle, and we just say southeast. We don't know if it's this angle or this angle. That's why we have to give blank of blank. Okay, let's solve for the angle. With that corresponding angle, what sides of the triangle do we have? Opposite and the adjacent. So that means we'll use what sine function? Tan of -1. Why do we have to use second tangent? Yeah, whenever we solve for an angle, we solve using the second button. The opposite side is 3,600. The adjacent side is 6,000. What mode should your calculator be in?
Degrees. Oh.
Degrees. Okay, check it out. If you don't know how to change that, it's in mode.
When are we ever going to use radians?
Never.
I have to call Brian, why use radians?
Yep.
So I always switch.
Pre-calc or calc, you use radians. Sorry. Okay, did I hear 30.9?
Yes.
30.9 degrees. So what is it? East of south or south of east?
South.
South of east. All right. Okay, and it's okay if you're feeling a little overwhelmed about this two-dimensional stuff. This is ahead of where we are now. I'm just kind of getting your feet wet a little bit so that when we get there, it looks recognizable at least. Okay? All right, first and foremost, if we want our velocity in meters per second, what do we need to do to our displacement? We go kilometers to meters. Exactly, we have to convert kilometers to meters. Oops. All right. And we've got to convert our time as well. So 32 minutes times 60 seconds. How many seconds is that? Thank you. All right. So solving for velocity here, we're going to take V equals d over t. So velocity is equal to 40,000 meters over 1920 seconds. Which gives us a final velocity of 20.8 Yeah? And what are our units here for velocity? Meters per second. Missing one thing? No. East. There we go. Velocity must have magnitude and direction. So our final answer is not 20.8 meters per second. It's 20.8 meters per second east. Magnitude and direction. So it's per, right? Every time we have a per something, that second unit has to go on the bottom. Okay, we're traveling 20.8 meters in 1 second. All right, so let's go from meters per second to kilometers per hour. So we know there's 1,000 meters in 1 kilometer. We know there's 3,600 seconds in 1 hour. Should get about 60 something. You got 70? Okay. 0.88 kilometers per hour. All right, good. And we're missing one thing still? East, thank you. 74.88 kilometers per hour. Okay, so I'm going to teach you a little shortcut for kilometers per hour to meters per second conversions. So you can use that. It takes out a lot of steps of that T-chart. Okay, so let's say that I give you a speed of 80 kilometers per hour, and you're trying to solve your problems. Okay, all your physics problems, whatever the problem asks for, but it's got to be in meters per second. Okay, so what we're going to do is put that in a T-chart. I'm going to walk you through the whole thing, and then I'll show you the shortcut. Okay, 80 kilometers per hour, we want to get it to meters per second, so we're essentially just doing opposite of what we just did, right? We just went meters per second, 2 kilometers per hour. So we'll say 1 kilometer is 1,000 meters, 1 hour is 3,600 seconds. That's how you convert from kilometers per hour to meters per second, right? We on the same page? Every single time that you do a conversion between kilometers per hour and meters per second, this part of your T-chart looks exactly the same. Wouldn't it? If you're going from kilometers per hour to meters per second, that part of your T-chart would look exactly the same. So what I want you to do is do just this part of the T-chart. Take 1,000 divided by 3,600 and see what you get. A little more specific than that. 0.2778. 0.2778 is essentially what you get when you take 1,000 divided by 3,600. This is your shortcut. So anytime I give you a value in kilometers per hour and you need to go 2 meters per second, you multiply by 0.2778. Okay, what if for some reason you needed to go the opposite direction? If you wanted to go meters per second, 2 kilometers per hour.
3.6.
You would divide, you would divide by 0.2778. You would do the opposite. Okay, divide by 0.2778. All right, so let's talk about speed. It's a little bit different than velocity in that it's a scalar quantity. What do we know about a scalar quantity? Only has magnitude. Scalars do not have direction. What was an example of something we've talked about so far that's a scalar? Temperature was one, yeah? What's one that we've looked at in physics? Time and distance. Distance is the scalar quantity of displacement. Okay, so speed is total distance divided by time. Remember that distance is different than displacement. Okay, total distance divided by total time. All right, speed has no direction, just a magnitude. So we would just be saying it's traveling 20.8 meters per second. We wouldn't need to indicate a direction in that case. Okay, speed would be considered an absolute value type of a number because speed would never be negative. The reason that speed is not negative because negative is an indication of direction in physics. Okay, negative is an indication of direction. So if speed has no direction, speed should never be negative. Okay, we don't work with speed very often. We work with velocity because it has a direction and it's a little bit more exact. I'll find myself using those terms a little bit interchangeably, but we're really mostly focused on velocity. Okay? Okay. Let's try another example. This example again, but we're looking for average speed. We looked at this problem a couple minutes ago and we solved for the distance already, so we did the hard part. Okay, we did this exact problem and we solved for the distance. So who in their notes can show me what that distance is or tell me what the go? Okay, and this is what we solved for earlier. So our distance traveled was 9,600 meters. The total time that it took, 2 minutes plus 2 minutes, so 240 seconds. Speed is equal to distance over time. Okay, it has the same equation for velocity, except you are not using a direction. You're not indicating a direction. So we need to take 9,600 meters divided by 240 seconds. — 40 meters per second. So why is it that those two values would be different? No. Not in any way, shape, or form. All right. Velocity's displacement over time. We're running 100 meters in 12.2. We didn't have to do any conversions. So tell me what our velocity here is. Say it one more time. One more time. Yeah? We agree? 8.2 meters per second. Okay? This 100 meters, we don't have a direction included in it. Okay? But since it's a positive number, we assume they're running forward, okay, or in the forward direction. That's what we can conclude that since we weren't given a cardinal direction, and it wasn't negative, so they weren't running backwards. We can assume that they're running in the forward direction, which means our velocity can just be positive 8.2 meters per second, or we could say in the same direction as the displacement, or something like that. But we don't need to include a cardinal direction if we weren't given one to start with. Okay? Position versus time graphs. These are for items that maybe do a lot of different things. They move and then they stop and then they speed up or they slow down. Position versus time graph is a little bit more complex motion. Maybe multiple things are happening here. So a position versus time graph allows us to look at an object's position during various times. So on a position versus time graph, we're going to be able to pinpoint what's happening not only at a certain time, but at a certain position. If the person is 4 meters from where they started, we can tell how long it took or what they're doing, basically. We're going to be able to look at position versus time graphs in a lot of different ways, and they can tell us lots of different things. All right. So here's a basic position versus time graph. And I've printed you out a couple of the ones we're going to cover in a second so that you can actually do the math on the graph, see what we're doing in class, and you don't have to take time to copy down the graph itself. So these are the ones coming up here in our notes. But position versus time graph. Position will always be on the y-axis. Time will always be on the x-axis. Always. Always, always, always. Time will be on the x. Position will be on the y. Position is most of the time in meters. Okay, so at a time of 1.5 seconds, they have traveled a total of 3 meters from where they started. Okay, this is their starting point all the way at 0. By the time we get to 6 meters away, it's taken about 3 seconds. Okay, we're going to be able to look at what a position versus time graph tells us. Okay, the slope of a position versus time graph tells us velocity. The slope of a position versus time graph tells us velocity. And we're not quite to the handout yet, so just keep going in your notes. Okay, the position versus time graph tells us an object's velocity because we are looking at basically displacement versus time. All right, so I want to show you why this is true. Why does the position versus time graph tell us velocity based on its slope? Okay. When we want to find a slope of a linear graph, what's the equation that we use? M equals y equals mx plus b is the equation for the whole entire line, yes. But m is the slope. How do you calculate slope? Delta y over delta x, right? Rise over run. That's how you calculate slope. Delta y over delta x. Are we on the same page? Okay, so now let's look at this particular graph. What of our variables is on the y-axis? Position or displacement. Okay, how far you are from where you started. That's what's on the y-axis. So if we plug in our variables, we would say this was delta d, right? The change in displacement is located on the y-axis. What of our variables is located on the x-axis? Time, so delta t. What does this equation right here look like? It looks like velocity. So that is why the slope of a position versus time graph tells us velocity. We're able to look at the change in displacement versus the change in time. Okay, bless you. Slope tells us velocity. That's something you've got to remember, and you've got to know how to calculate it. Okay? So our slope of a graph tells us velocity. What's the negative slope mean here for this graph? If I have a negative slope here, what's it mean that I'm doing?
You're going backwards.
I'm going backwards. Very good. Very good. Okay, so let's talk through what this particular person is doing. All right, from 0 to 2 seconds, what are they doing? Nothing. They haven't moved at all. Their position has not changed. So for 2 seconds, they stood still at their original starting point. Okay? I need you to look at this graph so that you can understand the motion that's happening with it. Okay? So from 0 to 2 seconds, they stood still. From 2 seconds to 5 seconds, what happened?
Back 3 meters.
They went backwards. Okay, they moved backwards 3 meters in that 3-second time frame. From 5 seconds to 7 seconds, what happens? They moved in the forward direction until they ended up 2 meters in front of where they started. Okay, they walked in the forward direction because our slope here is our velocity and it's positive. That means we're moving in the positive direction. Okay, are we good? Are we understanding so far? Okay, what about this right here? they just stood still. They just stood still. Their position remained still at 2 meters. 2 meters from where they started. Okay? This right here, we already talked about. What did they do here? They walked backwards. Here, what did they do? They moved forward again in the forward direction because our slope is positive. When the slope of a position versus time graph is positive, that means we have a positive velocity, which means we are moving in the forward direction. Okay? Even though we're still technically behind or in the negative side of where we started, we were still moving in the positive direction during this time. Okay? Are we getting it? Okay. We stood still here for just a little bit. What did we do here? We moved forward back to where we started, and then we stood still for 1 second. So our displacement overall on this graph was what? How far did he end up from where he started? 0. He did all that work for nothing. No displacement. Okay? All right, let's take a look at this position versus time graph. This is the second one on your handout. We're going to do some math with this one. Okay, so I want you to find the velocity. Okay, so what is the velocity from 1 second to 3 seconds? That means I want you to look at that specific time interval and calculate the velocity for me. All right, if we're going to calculate slope from here to here, it's delta y over delta x. So we need to start with our final, which is 60 minus 20 over 3 minus 1. Right? Final minus initial. So your final y was 60. Your initial y was 20. Your final x was 3 seconds. Your initial x was 1 second. Did we do that correctly? Okay, it's final minus initial. So you've always got to start with your final and subtract your initial. Rise over run. So that means we had a positive slope or a negative slope? We had a positive velocity because, look, our slope is positive. And our positive velocity should have been 20 meters per second. And it's positive. Okay, that means we were moving in the forward direction. Okay. Let's go ahead and try and find now the velocity from 4.5 seconds to 6 seconds. 4.5 seconds to 6 seconds. Okay, which is right here to right here. Let's find velocity of this person at that time. This time, what do we think about our velocity? Should it be positive or should it be negative? It should be negative, right? Because our slope is negative. Good. So to calculate this, we will take 20 minus 60 over 6 minus 4.5. Okay, which gives me 40 over 1.5. What do we get? Someone raise their hand and tell me what they got for velocity. What do you got? Negative 26.7 meters per second. And the negative here tells us it's going in the negative direction. Okay, or they're moving backwards. Okay, you should or hopefully will start to become really, really good at position versus time. Tell me the velocity of portion C on this graph. Tell me the velocity of portion C on this graph. I think it stops at 10, yeah.
You just lost yourself.
Good. I had negative 0.25 also. Negative 0.25 meters per second. We agree? Okay, tell me what the velocity of section B is on this graph.
0.
Yeah, good. Velocity of B is 0. There's no change in position here. No change in position. So he's standing still. He's not moving. There's no velocity. Okay? The slope should tell you that because there's no slope. So that means there's no velocity. But you also can see that his position's not changing. And if you know what velocity is, change in position over change in time, you know that you have no velocity there. Okay? What if I asked you for what's the displacement at B? What's the displacement at section B? 30 meters, exactly. If I ask for displacement at B, for time interval B, if I ask for his displacement, he's 30 meters away from where he started. He might not be moving, but he's 30 meters away from where he started, and he's standing right there. So displacement of a position versus time graph means you just read the axes of the graph. You just read where the graph is at that point. Okay? All right, how do you feel about that?